All right, guys, so we're moving on to 4.2 today. So 4.1, the video is up from last week. So if you get a chance, watch it. If you do have any questions over it, please let me know. We can go over any questions that you do have. Now, what we're looking at today is exponential functions. Now, we have two general types, exponential growth and exponential decay. Now, the reason we consider them to be exponential is because the amount of change from one term to the next, as we look at, say, a chart of x and y values, as the x values increase, so we can start at 0, 1, 2, 3, 4, the amount of change in the y values is going to increase drastically as we go from one to the next. Now, for any of these functions are going to come in the term f of x is equal to b to the x, where b is greater than 0, and it's going to be different than 1. Now, main reason we say it's different than 1 is because, well, if we said y equals 1 to the x, well, 1 to the 0 is just 1. 1 to the 1 is, it's not 0, is 1. 1 to the second is 1. All of these would be 1. So it really doesn't give us anything. And if we took the graphing calculator, we can say y equals 1 to the x graph. We just get a straight line. Table. We just get ones. Now, we also have to say that it's greater than 0. Because if we took, say, negative 2 to the x and graphed it, we get this here. Now, it doesn't show us a graph because it's not necessarily a function. It's not a continuous function for sure. Because if we look at the values, so at 0 it is 1. At 1 it's negative 2. At 2 it's 4. We're jumping from positive to negative. We're jumping from one side of the function to the other. We're jumping. So there's not a continuous function for it. So we can't have b be negative. It is possible, but we just don't have a continuous function. Now, one of them that we can do is say 2 to the x. So if we plugged it in, 2 to the 0 is just 1, because anything to the 0 is 1. 2 to the first is going to be 2. So we increased, not so much by 2, but we have a difference of 1. 2 squared is 4. 2 to the third is 8, difference of 5. 2 to the fourth is 16. 2 to the fifth is 32. 2 to the sixth is 64. And we see that we're starting to increase pretty quickly. And that's just for 2. Now, if we said 5, and plugged it in for this here, no, we don't need those, because that's going to be 5, 25, 125, 5 carry the 2, 625. So we can see here with 5, the amount that is differing from one to the next is increasing faster and faster. This is why we call it exponential. And if this is, and we'll get into more of this between especially exponential growth and exponential decay. Now, the first thing we're going to do is graph the functions. And when you graph them, we really just need several points and an asymptote. Now, this is on the next page. At the top of the next page, we do have all this information. Now, we consider it exponential growth or decay if b is greater than 1. If b is greater than 1, it's increasing exponential function, and it's going to be considered a growth. If b is between 0 and 1, it's going to be considered decreasing, and it's going to be considered exponential decay. Second part, the domain is the set of all real numbers, negative infinity to infinity. The domain for any exponential growth or decay function is this here. The range for the basic exponential growth function is going to be 0 to infinity, unless we reflect it across the y-axis, or not y-axis, x-axis, then it would be negative infinity to 0. But we do have this horizontal asymptote at y equals 0. Now it can be moved up and down, but the function just can't equal 0. There's no way to get there. And the function passes through the point 0, 1, because f of 0 is equal b to the 0, which is 1. So if we look at this here, 2 to the x. Now, one of the things that we're going to have is our horizontal asymptote. That is going to be y equals 0. Now, part of the reason we know it's y equals 0 is because there's nothing added or subtracted from the function, it's just 2 to the x. And then we just need some points. Now, we can graph it here, and we see 2 to the x does not cross the x-axis. There is no 0 for it. And I can create these two here. We have these two lines. Now, the reason I do this is because, as we've seen already, we can do second trace intersect to see where they cross. Enter, enter, enter. There's no sign change. There's no change where they're going to cross, where these two are going to intersect. So what that's telling us is that there's no way for the blue, our y equals 2 to the x, is going to intersect the x-axis. That is our horizontal asymptote. And in Alex, when you're graphing it, you're going to need this asymptote. Now we just need some points. Well, I do know what one of the points is. One of them is 0, 1. That's another point. 1, 2. We also have 2, 4. We also have 3, 8. We have negative 1, 1/2. And that's the function. So most of the points that we need to graph it, we can get straight from the graphing calculator. So we get 1, 0, 1, 1, 2, 2, 4, 3, 8, 4, 16. We can plot a bunch of these points here, tell it to graph it, and we're done. But we do need the horizontal asymptote. Questions on this here? Let's look at the next one, 1/2 to the x. We'll still have a horizontal asymptote at y equals 0. Because I can come into the graphing calculator, clear this out, parentheses alpha y equals enter 1/2 to the x, and hit graph. And again, we can do the same thing I did on the last one, 0. Do second trace intersection. There are no sign changes. So there's no place where these two graphs are going to cross. There's no place that's going to intersect 0, y equals 0. So it has a horizontal asymptote at y equals 0, the x-axis. And now we just need some points. Well, at 0, we are at 1. At 1, now we're at 1/2. And then we're going to be at 1/4, and then 1/8. And it's going to keep going down. Now at negative 1, we're now at 2. At negative 2, we're at 4. At negative 3, we're at 8. And it's going to get really close to that line. kind of came back up, but it's just getting closer and closer to that horizontal asymptote. And it'll never cross it. It'll never intersect it. Any questions on any of this here? Graphing these are pretty nice. They're pretty easy, especially in ALEKS, because we just need points in the horizontal asymptote and we're done. Now we have most of these here. Now, okay. That's right. Let me look at the domain and range of each of these here so that we have it. We'll look at some of the other functions too. Now the domain for this here is going to be all real numbers. Domain's all real numbers. For any of these here, the domain is going to be all real numbers. Now the range are the y values. Now we said it cannot cross y equals 0 here. So we have a parentheses 0. And it goes up, so it's going to infinity. And incidentally, the same thing is true for our other function. Domain is still all real numbers. The range is still 0 to infinity. Questions on any of this here? Now, with these here, we can shift the function left or right. Now, the movement to the left or right is going to be in the exponent, x minus h. And it's the opposite of what we think, just like inside parentheses. So if we have x minus 4, it's actually moving it 4 units to the right. If it's x plus 4, it's moving it 4 units to the left. If we add or subtract something to the outside, it's moving the function up or down. And that will also shift our horizontal asymptote. So if we have plus 3 to the function, it's going to move the horizontal asymptote up 3. Or minus 3 will move it down 3. And then A is a reflection across the x-axis, where we can have vertical or horizontal stretch too. Okay. So if we look at this function here, f of x equals 3 to the x minus 2 plus 4. Now this here, this function that's given to us is the function f of x equals 3 to the x. That's what the function is. That's the function they gave us. Already graphed. Now in ALEKS, it's going to be a little bit nicer than this here, because for ALEKS, you can just grab this function and move it accordingly. Now, the minus 2 is telling us we're moving it 2 units, where? Almost. Right. To move it 2 units to the right. Because here, x minus h, so h is greater than 0, it's to the right. Since it's still minus, h's value is actually just 2. Now, the plus 4 is going to move it where? 4 units up. Because with the x, it's going to be the opposite of what we think. So minus 2 is going to be 2 units to the right instead of to the left. And the number added to it, up and down, is going to be exactly what we think. So for our main point here, this here is going to be our 0, 1. We're going to move it 2 units to the right and up 4. So we're going to use 2 to the right and then up 4 will put us at 2, 5. So that's all I had to do to move it. And every other point is going to go accordingly. So -2, 0, here. I think that's too high. 1, 2, 3, yep. And we get this here. Now, also with the horizontal asymptote, our original horizontal asymptote was y equals 0. But we moved the entire function, what? Up 4. So the new horizontal asymptote is actually going to be at 4. Let me pull that up. Now, if we look at the graphing calculator, so I can say 3 to the x graph. So this is our 3 to the x function. Now here we could say 3 to the x minus 2. So this is just moving it 2 units to the right. We can see the whole function shifted 2 units right. And on the table, at 0, we have 1. But if I move 2 units down, now at x equals 2, the y value of the red function is 1. It's shifted everything 2 units right. But that's not all we had. We also had plus 4. So it's moved everything to the right 2 and up 4. And that's it. Now the domain and range of this function. The domain of our new function is still negative infinity to infinity. Our range. Now the function is still going up, so the biggest value we can have is infinity. What is the smallest value we can have? 4. And that's it. Questions on this here? Now the range doesn't always have to be 4 comma infinity, because what we can do is I can put a negative in front of it, and now it's going down. So the range would be negative infinity to 4. Now this here is a little bit different. Y equals negative 3 to the x minus 2, because the negative is not attached to the 3. If it had parentheses, then it would be. Really what this is saying, negative 1 times 3 to the x minus 2. That's really what it's saying. The negative is on its own. Questions on any of these here? Now I threw in the other one here, e to the x, because this is still another exponential function. It's just given to us by the value of e. Now interestingly enough, e is just a number. E is given to us by 2.718281828, and it continues on. It's another irrational number. And we could graph it pretty easily. Clear both of these out. As we can say, second ln e to the x. And we get this here. Now, e to the 0 is 1. So we do have this nice point. But if I wanted to graph any of these here, we could say e to the first, e to the second, e to the third, because the graphing, or Alex will let you do that in the function for plotting a point, 2 comma e to the second, to plot the points, and then graph it from there. And again, the horizontal asymptote for this one here is y equals 0, because we're not adding or subtracting anything from it. If we'd have subtracted 2 from it, our horizontal asymptote would have been y equals negative 2. Because it moves the entire function down 2, so the horizontal asymptote would move with it. Questions on this here? Now, the last thing we're going to deal with is kind of real-world application problems. And most of these real-world application problems, you're just applying parts of the function to it. Now, some of the problems already give you the equation to start with, and then you're just plugging in for the given values and solving. So now we have three main equations here. Simple interest, which is our I equals PRT, principal, rate, and time. Then we also have I is equal to, or the amount, is equal to principal times 1 plus R over N to the NT, where A is our amount, that our kind of value that we'll have, T is our time, N is the compounding period, how many times interest is taken. So either quarterly, monthly, weekly, daily. And the last one is continuous interest. A is equal to PE to the RT, or PERT, where P is our principal, what we're starting out with, R is our rate, and T is our time. Now looking at this here, so A through D, we're going to use A is equal to our principal, parentheses 1 plus R over N to the T. Now our starting equation, A, is what we're going to find, is equal to our principal. So they suppose that $5,000 is invested, so our principal, what we're starting out with, is $5,000. 1 plus our rate is 6.5%, but we need this as a decimal, so we have to move the decimal 2 spots to the left. 0.065. Now, N is the amount that we have compounded. So compounded annually, so every year. So it's going to be once. And lastly, determine the amount after 10 years with each option. So 10. So the first thing we're going to find is actually the compounded annually. And we're just plugging this in. So we can grab either calculator and say 5,000, parentheses 1 plus 0.065 over 1 to the 10th. And we can plug it in and get our answer. So $9,385.69. $385. So if it's compounded annually once a year, it is $9,385.69. Any questions on how we did the first one here? So quarterly, how many would it be for quarterly? Quarterly would be what? 4, because we're talking about quarters, so 4 times. So every 4 months, well, every 3 months, 3, 6, 9, 12. Where do we get an amount? So we can take the exact same equation and switch the 1 to 4. Seems very odd. Where n is the compounding period per year. $5874.56. NT, yep, that's right. Thank you, because I'm like, that seemed way too small. It didn't matter on the first one because, well, it's just multiplying it by 1 times 4. There we go, 9527. That seemed way too small. Point 952779. Because I'm like, that should have increased. Thank you. Yep. NT. Now we can look at the next one. $5,000. 1 plus 0.065 to the 10th. But the next one is monthly. So our n would be what this time? 12, because 12 months in a year. So now we're going to switch the n in our equation to 12. And again, we should expect the amount to go up. 9560.92. Questions on this so far? Now, daily is going to be what? So we're going to switch the n to what instead of 12? 365. $95.77.15. Now, compounded continuously is our, what I consider or call PERT, because that's kind of what it looks like, P-E to the RT, PERT, where P is still our principal, our 5,000, E, and we have our rate, 0.6 or 0.065 times our time, 10 years. And we can do this in a calculator. We can say 5,000. Second ln to get E, 0.065 times 10. Enter. $95.77.70. So continuously and daily is very close to the same amount. Questions on any of this here? Now, a lot of the other problems that give us equations is just plugging in the information that we are given. So if we look at this here, the half-life of radium-226 is 1,620 years. In a sample originally having 1 gram of radium-226, the amount A at T in grams of radium-226 present after T years is given by this equation here, this half-life equation, where T is the time in years after the start of the experiment. How much radium will be present after each of the following years? And in each one of these here, we're just plugging in the amount for T. So for A, we're saying A sub T is equal to 1/2 of 1620 divided by 1620. Anybody have a guess at what that's going to be? Because 1620 divided by 1620 is what? 1. So we'll just have 1/2 to the 1, or just 1/2. Our next one is at 3,240 divided by 1620. Do you think this number is going to get bigger or smaller than our previous answer? So 1/2 to the 3240 over 1620. And we get 1/4. It should be going down. Because 3240 divided by 1620 is 2, so we have 1/2 squared, and we get 1/4. And lastly, we have 4860 divided by 1620. And again, we can plug this into the calculator, and we're going to get 1/8. So we have 1/8 the amount. So we have 1/8 of a radioactive gram of radium after 4,860 years. Radium is very radioactive and takes forever for it to fully dissipate. Y'all know who was the, not creator, but who discovered radium? Madame Curie? Yes, and she's the one that founded it or discovered it, and they found it actually very interesting because it's a rock that naturally glows. And ended up, her and her husband both died of radiation poisoning because they didn't know at the time it was deadly. They just thought it was an interesting rock that glowed. And her husband actually had a massive paperweight of it just sitting on his desk. All of their stuff, their research notes are still radioactive. But that's about it, yeah. They didn't realize it was radioactive and ended up homework.